Hey guys, today we're taking a look at our notes for 3.3, which is all about solving three variable systems of equations. So before we hop into our new stuff, let's do a quick recap of solving algebraic systems when they are 2 by 2, because we do want to make sure we have those skills sound before we jump into applying them to a three variable system. So looking at our first box here, we're solving by substitution. Remember, when we are using substitution to solve a system, we are taking what we know one of my variables is equal to in one of those equations and replacing that same variable in my other equation. So in this box one problem, we have my bottom equation has x equal to y plus 1. So we've already got x isolated. That's great. That is going to be a key identifier that substitution is going to be the easiest method for solving that problem. So once I know that that's what x is equal to, in my top equation, I'm going to replace that x value with what I know it's equal to, y plus 1. So as I go through and do that substitution, I'm just replacing my x value with y plus 1, and the rest of my problem I do not change for that top equation. So once I've done that substitution, now I'm just going to go through and solve that one variable equation by distributing my 2 into y plus 1. So we end up with 2y plus 2 plus my y value equals 5. I can collect up my like terms for my y values on the left. 3y plus 2 is equal to 5. And then I go through and solve for my y value by subtracting 2 on both sides. 3y equals 3. And of course I divide by 3 on both sides and get my y value, my y value of 1. Just like in any other system, once I have my first solution, I can go back to one of my original equations to plug it in to find my other answer. So I'm going to take that y value of positive 1, go back to that original equation, which was x equals y plus 1. So if x equals y plus 1, that means x equals 1 plus 1. So my x value is 2. And of course, just like always, we need to make sure it's an ordered pair for our solution. I can't just leave it as my two separate answers because this is representing the solution for my system where it's an x and a y value. Okay, so that was solving using substitution. And I'm taking what I know one of my variables is equal to, replacing it in my other equation for that same solution. Our other algebraic method of solving was elimination. And this one was where we were getting two of our variables to cancel out or eliminate by having this exact same coefficient but opposite signs. So I recognize in this one right away that my x values, if I added my equations up, would cancel each other out. Right? Negative x and positive x add up to 0x, so my x values go away. So it's already set up for us for elimination that if I just added my equations up, those x values cancel out. I'm left with 5y if I collect my like terms. 1 plus 4 is 5. And so really quickly, we end up with y equal to 1. Now that was really nice in that case because my variables already matched up, which is a great, again, thing to key in on if that's going to be a good choice for you. And remember, in those algebraic methods we did before, for some of our more advanced problems, you might need to manipulate some of those equations to get your coefficients to match up, one positive, one negative of the exact same number. But just like in box one, once you have your first solution, you can go ahead and plug that back into one of your original equations to solve for my x value. So I'm going to take it back to my original top equation because that one was just x. So in that original top equation, it was x plus 3y equals 1. So that would mean x plus 3 equals 1. So when I subtract 3 on both sides, I end up with negative 2 for my solution. So that tells me that negative 2 comma 1 would be my final answer. Right, so that's a recap of our two variable systems, right? Those algebraic methods that we did for solving two variable systems, substitution and elimination, they both have their merits. You both have the choice between those two when you're solving a 2 by 2. Okay, now, flipping our notes on over, down to box 3 and 4, we are getting into solving three variable systems. So this is the new thing that we're talking about today. So with three variable systems, you can see I have an x, a y, and a z value that I'm solving for. And because of that, we need a third equation to be able to solve for that. That is something that's based on what's called the fundamental theorem of algebra that says however many solutions you're looking for to solve, you need that many equations in order to be able to appropriately solve for all three of them. Okay, and how we'll handle this is a bit more complicated than a two-variable system, but it's the same concepts, right? In a 2x2 and a two-variable system, we were taking and using substitution or elimination to get it from two equations with two variables down to just a single equation with a single variable that we could solve. We're going to do the same thing with a 3x3, but we have to do it multiple times. So we're going to have to start off by getting it from a three-variable, three-equation system down to a 2x2, or a two-variable, two-equation system, and then repeat that process over again like we had done with our 2x2s on the front page. Okay, so that's going to look different depending on if you're going to do substitution or elimination. I'm going to show you one of each. For this first one, I'm actually going to show you elimination. That is the one that is, I think, more consistently clean answers. You're a little bit more guaranteed not to have to deal with fractions or decimals in your problem. So I actually tend to use elimination the most often when I'm dealing with a 3x3 system. And the idea here is that I'm going to try and pick out an x, a y, or my z values to be able to manipulate these to get them to, again, eliminate, right? I'm trying to get rid of my coefficients, one positive, one negative, for those numbers to get matched, so that when I add up my two equations, they're going to cancel each other out. So I look to see, when I'm starting my problem, is there a set of them that I could easily turn into each other, right? Just like when we were doing those solve elimination problems algebraically for a 2x2, I was trying to see, is it easier to get my x coefficients to match up, or is it easier to get my y coefficients to match up? So in this case, I've got my choice. I would say I'm choosing realistically between my x's and my z's for this problem. Or sorry, my x's and my y's, because I can turn this 2 into a 4, right? I could turn this 2 into a 6, so that would be an option for me. I could do it that way. I could also choose my y values, because I could turn that negative y in my bottom equation into a 2y and into a negative 3 to get them to cancel out, right? Those would be my two choices. It's not impossible to do my z's here for my elimination, but it's a lot harder to get 3 and 5 to be the same number, 3 and 4, or 4 and 5 to be the same number. In that case, you'd have to be multiplying both of your equations to get them to cancel out, so I don't want to go down that path. In general, I usually go with the equation that has just a single equation or a single variable that doesn't have any coefficients on it as the thing that I key in on to be able to use for elimination. Because what we have to do for these is I'm going to pair up one of my equations with the other two to get that variable to cancel out. So we kind of use the same equation over and over again. So I call it the eliminator, right? I take this bottom equation, I'm going to call this the eliminator, because I'm going to use that to eliminate my y values in the other two equations. So I'm going to take that bottom equation I have highlighted in blue, I'm going to pair it up with each of my other two to cancel out the y values. Okay, so we're going to have to do this in two different steps, two different stages, because I have to pair them up. I'm not trying to get them all to match at the exact same time. I'm just trying to pair them up two at a time to get my one variable to cancel. So in this case, because I'm going to choose my y values to cancel out, I'm going to take that top equation. So I'm going to do this in green. So my original top equation was 4x plus 2y plus 3z equals 12. And then this bottom equation was 6x minus y plus 4z equal to negative 3. So 6x minus y plus 4z equal to negative 3. But they would not cancel out the way that they're written right now. Right? I have to manipulate this equation to get my y's to cancel. So since my top equation has a positive 2 for its y value, I need my bottom equation to have a negative 2 in order for them to cancel. So that would mean that this equation becomes, right, my 4x plus 2y plus 3z equals 12 stays the same. My bottom equation becomes 2x minus 2y plus 8z equals negative 6. And so when I add them up, my y's cancel out. 16x plus 11z equals 6. So I've taken that three-variable equation, those pair of three-variable equations, and gotten it down to just x's and z's. Okay, so once you've done that with your first pairing, you're going to have to repeat that process over again for the second pair. So that was my original top with my bottom. So I'm going to do that same process with my middle equation and the bottom one. Okay, so I'm going to go down and give myself some space because I don't think I have room to move over to the right. Nope. Okay. So I'm going to do the same thing with my middle and my bottom. I'm going to do the same thing. So I'm going to start with green here. So we've got 2x minus 3y plus 5z equals negative 7. My original bottom one was still 6x minus y plus 4z equals negative 3. And so in this one, to get my coefficients to be the same, one positive, one negative, I have to multiply my bottom equation by a negative 3, right? Because I need my signs to be opposite. And since my top one has a negative 3, I want my bottom y coefficient to be a positive 3. So when I do that, that gives me 2x minus 3y plus 5z equal to negative 7 up top, negative 18x plus 3y minus 12z equals positive 9 down below. And so when I when I add them up, I end up with a negative 16x minus 7z equals 2. Right, so negative 16, because that'd be 2 minus 18 is negative 16x. All right, so now that I've done this, these two equations right here, my 16x plus 11z equals 6, and my negative 16x minus 7z equals 2, is a two-variable system. So I'm going to rewrite this down below, but this is the exact same type of problem that we just did on the front side. All right, we've got a 2x2 system that I can solve using either of those two methods. I could solve using substitution, or I can solve using elimination. But I've got it down to just a 2x2. So now that I have it down to a 2x2, it's the exact same skills. This one, definitely going to be an elimination problem. Just like that problem in box 2, we already have my coefficients matching, one positive, one negative. So those 16x and negative 16x's cancel each other out. 11 minus 7 would be 4z. 6 plus 2 is 8. And so as I go through and finish this problem off by dividing by 4 on both sides, I get my first solution, which is positive 2. So just like in any other system problem, once you have your first solution, you need to work your way back to get your other answers. Now in this case, because I have 3 variables that I'm solving for, now that I have my first one, I have to go back to an equation that has this z value and just one other equation. So I have to go back to one of these, the bottom pink equations, or what I have here in this like purple. I have to go back, plug my z in for positive, like 2 in for positive 2 in for z, and then solve for x. So I'm going to do that here in this top equation. So if I plug 2 in for my z value, that gives me 2 for z, right? 11 times 2 equals 6. So 16x plus 22 equals 6. I subtract 22 on both sides. I end up with 16x equals negative 16. Divide by 16 on both sides, and I get that x is negative 1. And so I've got x, I've got z. I just need to get back somewhere where I can find my y value, and this is where I have to go back to one of my original problems that were printed on the page. Right, I have to go back to an equation that has x, y, and z, so I can plug in x and z to solve for my y value. And I'm going to go back to that eliminator problem all the way back at the bottom of my original 3, because that one is just negative y, so it's going to be the easiest for me to get by itself. You also could go up to the top one, since those are all nice positive numbers. That might be easier to handle, but just for the sake of cleanliness, we're going to go ahead and plug into that bottom one. So I'm going to plug in negative 1 for my x value and 2 for my y value in that original bottom equation. So that original bottom one was 6 times my x value minus my y value, just eraser, there we go, minus y, plus 4 times z equal to negative 3. Right, that's just my 6x minus y plus 4z equaled negative 3, with negative 1 for my x value and positive 2 for the y. So that gives me negative 6 minus y plus 8 equals negative 3. So when I collect my like terms, because negative 6 and 8 are on the same side, we end up with negative y equals, negative y plus 2 equals negative 3. So negative y equals -5. So my y value is +5. And you can see in this problem, I've got all three of my solutions sitting right on my screen without having to move anything around. But just like in our front two pages or our front two problems, it has to be in an ordered pair. Now I can't do an ordered pair because I have three solutions, so I have to use what's called an ordered triple. An ordered triple is x, y, z. So in this case, my final solution would be -1, 5, 2. And that is my final answer. That right there, that ordered triple is my solution. Okay. Quite a bit more complex than that front side problem, and that is just the belly of the beast. That is just kind of how it is with a three variable system. We're going from a three variable system down to a two variable system, right? That's what those steps were down here in green and pink. Right, I took my three variable system, translating it down with elimination to get it down to a two variable equation. And then once I had my two variable equations, I just lather, rinse, repeat from what we did on the front side. Right, what we did in our algebraic solving of 2x2s is all we got to do from there. Okay, so that is one of the options. Right, solving using elimination is one of the options, and really, again, elimination versus substitution for these problems is just how you go from a 3x3 down to a 2x2. And that again, three variable, three equations down to a two variable, two equation. If you are not a fan of that, we also do have substitution as an option. So I'm going to do substitution for this one. So I'm going to put that as my note here that we are doing substitution. I don't need to do that in sparkly ink, but my computer is lagging a little bit right now. All right, we're just going to switch substitution. Okay, so in substitution, just like box 1 on the front side, I'm going to take what I know one variable is equal to in one of my equations and replace that same variable for the other two equations. So in this case, I'm going to look to solve for either x, y, or z in one of my equations in order to then replace that same variable in my other two equations. And looking through these, again, you want to be strategic on what you are going to choose to get by itself. You want to choose the one that's going to be the easiest and cleanest to get isolated. So if you have any parts in your problem where it's just x, just y, or just z, that's the one you want to go with. So in this case, I am definitely going to solve for z in this bottom equation. It is the only option that we have here that I won't have to do any division by, and it's going to be only like 2 steps to get that variable by itself. All of my other variable terms have coefficients next to them, so they're going to require division to solve. So I'm going to solve for z in this bottom equation, and to get z by itself down there, I would subtract 2x from both sides, subtract 4y from both sides, in order to get z by itself. So that tells me this bottom equation, if I rearrange it to get z isolated, I would end up with 6 minus 2x minus 4y. So now that I have z by itself, I'm going to take what I know z is equal to, and in my other two equations, I'm going to replace that z value with 6 minus 2x minus y. So I'm going to do this one step at a time just so we can plug it in and clean up our answer a little bit before I get too much going back and forth between equations. So over here on this left side, I'm going to do that with my original top equation. So that was 3x plus 2y minus 3 times, and now I'm going to put that in for z, right? 6 minus 2x minus 4y equals -2. So I'm going to go ahead and clean up this equation. Right? This is now just a 2 variable equation. It's just x and y's. So I can go ahead and rearrange and do my thing to clean this up. Right? I'm going to have to distribute my -3 into that parenthesis. That gives me 3x plus 2y minus 18 plus 6x plus 12y equals -2. And so I've got 3 and 6x, which is 9x. I've got 2 and 12y, which is 14y, minus 18 equals -2. And so my last step to get this kind of in standard form, how I'm used to seeing it, would be adding 18 on both sides to get that 9x plus 14y equals 16. Right, so that was my original top one. I'm going to do the same thing, but in red for my middle equation. So over here for my middle one, I'm going to draw a little squiggle line just to keep it separated. 7x minus 2y plus 5 times 6 minus 2x minus 4y equals negative 14. Kind of ran out of space there. I'm a little bit off the page, but that's all right. So 7x minus 2y, and now distributing in, gives me 30 minus 10x minus 20y equals negative 14. And then I can start collecting up my like terms. So I've got 7 and negative 10 for my x values, which is negative 3x. Negative 2 and negative 20 is negative 22y. Plus 30 equals negative 14. And so when I subtract my 30 on both sides, I end up with negative 3x minus 22y equals negative 44. Okay, so I've gotten it down to a 2 by 2. Right? I've got an equation that's just x and y, and an equation that's just x and y. So from here, it is the same no matter which of my methods I'm using. Right? This is just what the beginning steps look like if you're going to solve by substitution. If you're solving by elimination, then you pick out your eliminator, pair it up with the other two to cancel out whatever variable you're canceling out. Right? But now that this is a 2 by 2, from here, it is the same thing we did on the front side. All right, so I'm going to rewrite these down below here so that I can solve this using a regular 2 by 2 method. So 9x plus 14y equals 16, and negative 3x minus 22y equals negative 44. Okay, so this one still set up, I would say, probably for elimination. We're going to have to do some hardcore rearranging and probably deal with some fraction work to be able to get any of these x or y's by themselves. But relatively easy enough to get my x's to cancel out here. I can just multiply this bottom equation by 3 in order to get my x's canceled. Because my top one being positive 9, I can make my bottom equation a negative 9x, and I would have them canceled out. So if I do that, my system becomes 9x plus 14y equals 16, and then negative 9x minus 66y equals negative 132. Okay, so I'm definitely going to have my calculator handy here because I can see in a second when these 9x's cancel out, I've got 16 minus my 66 for my x or my y value, and then 132 plus my 16 for my constant. All right, so negative 132 plus my 16 gives me a negative 116. Oops, 116. And then 66 negative and 14 gives me a negative 52 for my y value. So if I take that 116 and divide by 52, I'm going to end up with a fraction. But in this case, if I divide by negative 52 on both sides, my negatives cancel. I can reduce that fraction, but that y value only reduces to 29 over 13. Which, again, you can use your calculator on that. I could pull up the calculator and show you again. Just do your negative 116 divided by negative 52, and then it's going to give you a decimal. It should come out to about 2.23. So math, enter, enter, and that will give you a reduced fraction. Because remember, we need to either have our answers, if it doesn't tell us to round, as either a reduced fraction or an exact decimal. And in this case, your calculator is going to spit out a bunch of decimal places that we would have to round off in order for us to be precise. So that means our only choice for how we can have our answer written up in this one is a reduced fraction. So 29/13 is that y value. So this is going to be an ugly problem, but I wanted to expose you to one of those as well. But don't let that deter you from substitution as a method. Right? The only thing that is like the substitution stuff is our red and green steps on the screen right now. Right? Those two things that we did were substitution. The rest of this back down here in black and blue, that is just because this is an ugly system. It is not because we used substitution. It would have ended up being that way for elimination as well. Okay, but now that I have my y value, just like in every other problem, I'm going to go back to a spot where I can plug that in with one other variable. So I'm going to say that original, maybe that top equation is going to get me my number a little bit nicer, I suppose. But we've got, where were we? Let's do this in red. So 9x plus 14 times 29/13 equals 16. So I'm going to multiply those together. 29 times 14 divided by, oops, sorry, it was 106, sorry, 406. 29 times 14 is 406 divided by 13. Yep, that does not reduce at all. So we're going to go back to that. 9x plus 406 over 13 equals 16. So, ooh, man, this is ugly. Subtract 406 thirteenths from both, from both sides. So we've got 9x equals, and then 16 thirteenths would be 208 minus 406 thirteenths. That would be negative 198 thirteenths. And when you divide by 9 on both sides, which is the same thing as multiplying by 1/9, that reduces that 198 to a negative 22. So this is a 22 up here. So we end up with x being negative 22 thirteenths. Whew, all right. And then last but not least, we've got x, we've got y, we need z. So I need to go back to one of my original problems that were written up on the page. I'm going to go back to that original z after I rearranged. Z was 6 minus 2x minus 4y. So that was z equals, zoom back in here and do this in pink, 6 minus 2 times my x value, which was negative 22 thirteenths, minus 4y, which my y value I forgot to replace there was 29 thirteenths. So we end up with a total, again, I'm going to do this on my calculator and just kind of pause the video for a second and then come back. But this ends up coming out to a total of 6 thirteenths. 6 thirteenths is what it reduces to. So in total, we've got this ugly ordered triple of negative 22 thirteenths, comma, 29 thirteenths, comma, 6 thirteenths for my solution. Again, you are not going to have that level of ugliness on most of the problems, if any of the problems. That is just poor planning on Mr. Behrens' part. I gave you guys a problem that was quite a bit advanced, but still, like, the takeaway that you should have from this problem is that substitution step. So those reds and green steps made sense to you before we got to our 2x2, then substitution might be your preference. If that was not something that you enjoyed doing, if you didn't like having the big long equations as single, like 2 variable equations, then maybe elimination would be your preferred thing, where we did this in green and pink, where you paired up your one eliminator equation with the other 2, canceled them out and got them down to a 2 variable system, in which case then from there it is just solving however you would like to. So as always, if you guys have any questions, if you have any concerns, anything that you guys need help with, don't hesitate to reach out, and have a fantastic day. We'll see you soon.